Okay, so let's talk a little bit about the exam. Exam on Friday in this classroom, and then there'll be one other, and I'll send out an email of what the other room is and what the schedule, this university schedule to tell me. So we'll have plenty of room to spread out. Okay. I will allow you to bring one 3x5-inch card. You can write on front, back, around the sides if you want to write that small. Okay. But here's the concept. Be very aware of this. If you've taken classes from me, you'll know that if you think you're going to come into the exam and have a whole bunch of examples on this, and you're going to figure it out during the exam, you're not going to have enough time. Okay. The exam is to reduce the stress of, oh, I have to remember everything. And I know it may seem like it's been an ancient long time since I've taken the exam, but it really hasn't been that long. And I remember going to the exams and teacher handing them out, and I look at it and it says name, and I'm like, name who? Right? And the exams can be very stressful. So the purpose of the 3x5 card, even though everything should be up here, is to kind of relieve that stress and kind of jog your brain a little bit on that's what that equation was, all right, type of thing. I will provide any information like viscosities. If you need to use the Moody diagram, I will provide the Moody diagram. You know, you're not gonna have to do copies of tables of minor loss coefficients on there. Now, I kind of expect you know what the entrance loss and the exit loss are. Those are kind of given, just like I would kind of expect you to know what the specific weight of water is. Even though, you know, it does vary as a function of temperature, a lot of what we do, we don't care, and we just use the one value, 62.4, right? And the specific weight or density of water in the English system and in the metric system. Those kind of things should be up here, but your cards to help relieve that stress. So, in essence, 50 minutes, and what's going to be the concepts on the test. Oh, also no cell phone, smartwatches, earbuds, or multimedia devices. Just the standard test. The test will cover chapters 1 through 4 and parts of chapter 12, because we did flip back to chapter 12 to look at valves to get minor loss coefficients. Again, I'll provide those if needed, all right? But you should be able to calculate any of the fluid properties. Specific mass density, weight, gravity, viscosity, surface tension, bulk modulus, elasticity. Those will be likely part of other problems, not necessarily called out on their own, although I could. Hydrostatics. You know, I should be able to calculate pressure in a fluid, understand the difference between gauge pressure and absolute pressure, be able to calculate manometers, be able to calculate the pressure on a submerged gate, and apply the principles of statics, because that is where design really comes together, is when you're bringing multiple parts from different courses together. Even though, you know, we covered a lot of this in fluids, this is still, we're taking the principles of fluids and applying them to real world scenarios. Buoyancy is part of the pressures on a submerged gate or the forces. Momentum equation, find the restraining force. It could get a problem like the force on a nozzle, because you have to design the bolts, or the bolt's going to be strong enough to hold that nozzle on there. It could be a thrust block problem. So all these different things could be potential test problems. So understand those principles. Sometimes I like to couple problems, like the thrust block problem. I didn't ask you to do it in the homework, calculate the pressure at the outlet, because we hadn't covered the energy equation yet. Although you should have seen it from fluids, but I was going to ask you to do homework until I reviewed it. But in reality, you should be able to now do both momentum equation and the energy equation. You should be able to use them together to solve a problem. Okay. So you can use the energy equation to find a pressure, to find a velocity or a flow rate, and then you can couple that with the momentum equation to go ahead and find whatever the restraining force needs to be for whatever you're designing. You should be able to compute the energy correction coefficient or the momentum correction coefficient. All right. Flow in pipes. And this is a big chunk of what we covered, kind of the key things: turbulence versus laminar flow, understand the Reynolds number, conservation of mass, Q is equal to VA. That's used in a lot of different problems. The energy equation, you know, you should be able to compute the flow rate, the head loss, or the design for pipe diameter system. And I will tell you, there will be one of those problems on there. That's a given. There will be one of those three. I don't know which one yet, but you will have one of them. So just fair warning. You should be able to calculate the friction loss. Of course, that's part of what's above, but there are the different methods. The Colbrook-White, which I would not expect you to solve on an exam because it is implicit, but you should understand the Moody diagram, and you should be able to solve the Swami and Jain if you choose. Now, I will, if there is a friction problem on there, I will supply a Moody diagram. And if I tell you explicitly to work it using the Moody diagram, then I want to see your work on the Moody diagram. If I don't, then you can use either the Moody diagram or one of the equations. I don't care, okay? So all depends on what I'm trying to test you for. If I want to see if you know how to use the Moody diagram, I will say use the Moody diagram. Otherwise, you can use Swami and Jain. But you can always use Swami and Jain to check your work. Like, I'm not sure if I'm reading this right, punching this into the Swami-Jain equation, boom, falls right out. You know if you're pretty close. Minor losses, valves, entrance and exits, elbows, expansion, and contraction. Now, it would seem obvious that including a minor loss calculation in the energy equation up above, including the flow rate, head loss, or design for pipe diameter, would be a real-world problem. So that could be a nice combination of those two concepts. Because when we design most things out in the real world, they're going to have friction losses, they're going to have minor losses. Okay? So really the hardest thing that I have to do is find a problem that will allow you to show to me what you know within the time frame we have. That's the hardest part, within the time frame we have, right? Because I know that 50 minutes is just not a lot of time. So I have to figure out how to create a problem that is relatively short, but can still allow you the opportunity to say, hey, I know this material. I'm not trying to trick anyone. My job is to find out, is to assess what you know. And I know tests are a terrible way to assess. It'd be better if we could sit down one-on-one and do it. But, you know, I just don't have the time to do that. So we use tests. All right, Hayes and Williams. As much as I hate it, still need to know how to use it because you're going to see it out there. So you should be able to do the same three things with the Hayes and Williams that you did with the energy equation. Flow, head loss, or size of pipe, and then also equivalent lengths for minor losses. And then the last thing, HGL and EGL. Okay, you should be able to correctly draw those for a system, and I will get the homework post. I will get the solution posted, today's homework. I'll also get, oh, I think I did post the last, yeah, I just barely posted before I came to class homework number 10, which was the minor loss homework, and then I get back to my office, I'll post number 11 as well, okay? And this review sheet is posted to Moodle already as well.
Do we have any homework due Friday?
You will not have any homework due Friday. Depending upon how far we get today, you may have homework due on Tuesday, okay? But between now and this, the material we cover today is not on the exam. This will be on it. Well, it's not only on exam one. I'm going to be specific there. It will be on exam 2, right? So that's what I would like you to know for the exam. It's not much, right? Maybe a little bit, but you've seen most of this is in fluids, and so it's your opportunity to do well. All right. Any questions? Any concepts you like? You know, if you want me to cover a concept or work an example problem, work a homework problem, I'd be more than happy to do it.
You do the first part of the first question on chapter 10 homework.
Chapter 10 homework.
Or
Homework number 10?
Number 10.
Okay. The first part of homework number 10. Isn't this?
Or just go through it. I think I'm missing something on that one.
Okay. There we go. Okay, so we have this, this pipe has a globe valve, and it obviously has to go higher than the water level that's driving the flow. So we have a water level low level here, an outlet here. So we have a driving head that's driving head right here. H1 or H2, sorry, H2. Come on, I didn't erase. H2 minus H1. That's the driving head. But because the pipe is above our driving head, this means that A, we would expect A to be a vacuum, right? And that, in fact, is what we want to calculate for A. But before we do that, we want to calculate the discharge flow rate. So we're going to go ahead then and clean off this here. Oh, I guess I should have left that, but we can then go ahead and write the energy equation from this point over here to this point over here. So this is 1 and this is 2. And so I write the energy equation P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G is equal to P sub 2 over gamma plus Z sub 2 plus V sub 2 over 2G plus the head loss term, right? Now, the hardest thing about, well, I don't know if it's the hardest, but this head loss term is where most of the work is. Because if we look at this, we say that P sub 1 goes to 0. And if we set our datum down here, man, Dr. E would be so ashamed of me. I cannot draw a straight line. You know that NIST calibrates their straight line off of him, right? That's a joke, guys. Yeah. All right, so we have our water level over here, Z1 is going to be that H2 minus H1. And V sub 1 goes to 0. P sub 2 over here, it's a free discharge, so that's going to go to 0. Z sub 2 is going to go to 0. But V sub 2 is not, because there's still velocity going out that right there. Okay. And then we can go ahead and write our head loss. Now our head loss is going to be, our friction loss is going to be F L over D. And I'm just going to leave it in that form right there, F L over D. Plus then we have an entrance loss, so K sub E. Okay, plus then 4 times the K of the elbow. And last time we talked about how to get the correct value for that, because it's a threaded elbow, plus K of the globe valve. Okay, now do we have, here's an interesting point, do we have an exit loss here? Is the velocity changing? It's not. So there is no exit loss because the velocity is not changing. Now, in essence, this part up here, that's what we would be losing if there was a minor loss. So it's still kind of included, if you will. We just haven't converted it from a velocity to a pressure yet. Okay, but it's not typically down, or it's not in our equation down here. So that right there represents the friction and all the minor losses in our system. Okay, and we take all that and multiply it by Q squared divided by 2G A squared. Okay. So if we stick this then equals then the head loss. Oops. And that would go up here, right there. All right. So when we look at this, we say, okay, we know all these minor losses. We know the pipe size. We know the length. We know the diameter. Yeah, it's the size. We don't know the friction factor. We don't know the flow rate. So we're in the scenario now where we have to select a guess either the flow rate or the friction factor, and iterate until we get the correct friction factor. And then once we get the correct friction factor, we can solve for Q, and we'll now have the flow rate. Okay, Aaron, how are we doing with that? Where are we at? Is there one part of this or several parts that you're not?
Well, so I guess the way I went about it was, can we, instead of the Q squared over 2G8, can we use that as a V squared?
Sure. We can go ahead and
Velocity?
we can actually solve, yes, we can solve for the velocity down here. V squared over 2G. And then once this converges on a velocity, then we know that the flow rate is related to the velocity. How? Yeah. So yeah, you can put it in this form right here, solve for the velocity. And that actually is easier to solve for the Reynolds number, because it's velocity times diameter divided by viscosity. So yeah, that's easier. And then once you get velocity converged, multiply it by the area, and boom, there you got your flow rate.
What I'm saying is, can't you just, you've only got one term there, velocity squared, or is it different? Because the one term you don't have in the first equation is velocity squared, the same one down there on the head loss equation, are they not the same velocity?
Yes. So actually, by the time you solve this, I could actually come down here and bring this value down, and I could put this as 1 plus FL over D.
And so then you would just put 12 equals that equation and solve for V squared, or solve for V, for my, that's I guess what I'm missing, I solve for velocity that way.
So we still need an.
Yeah, 12 being H2 minus H1. Yeah. So this your head loss across your system does go to 12 when you solve your energy equation. And so yeah, 12 equals that whole equation, solve for the velocity, but you still don't know the friction factor. So you still have to iterate to find the friction factor. Because the friction factor is a function of E over D and the velocity, or the Reynolds number. And we don't have the velocity or the Reynolds number yet. So we have to
Can you
guess.
just get the E from the table?
We have E. Yeah, we have E. So we know that F is a function of E over D and the Reynolds number. We know that the Reynolds number is equal to the velocity times the diameter divided by the kinetic viscosity. So we know E over D, we're good there.
That's where I messed up, for some reason I thought just the friction was the over D, not a function, so that's where I messed up.
Yeah. So we have to know this and then use the Moody diagram or one of the equations to find the friction factor, and that includes the Reynolds number. Okay. So unless you're a really good guesser, you're not going to get the correct friction factor on the first time. So you'll probably have to iterate. Okay. Everyone comfortable with that? Other parts of this problem you didn't quite gather? And the second part then, once you get the flow rate, then you can do the energy equation from either end. You can go from 1 to A or from 2 to A, and it doesn't matter because we're assuming that A is exactly in the middle. Yeah, and that was given L is equal to 500. And so you can solve it going from any known boundary and get the value of A. It turns out A is pretty negative. It's a very high value. You probably wouldn't want to design a pipeline like that. Uh-huh.
What is a globe? A globe?
What's a globe valve?
Yeah, what is that?
So a globe valve it's a valve where the seat has been turned horizontally. Just a second. I don't know an easy way to clean this thing out. There's got to be one, but I just haven't figured it out. You guys seen any of the other faculty know how to clean that off with a touch of the button? You gotta get trained on. So there's the case, the housing of the globe valve. This is the seat that they're putting in there. Stem, and it's the stem that's going to go up and down on that seat. It's going to allow. It opens up, so now the water can come in and flow around that seat and out the other side. And is controlled by that opening that the stem makes as it moves up and down. What's that?
The diagram of the grass you want the question, like, is there the globe, where's the globe involved in that diagram? The picture.
Come on. Globe valve's right there.
So that's why we have the A globe, right? We find the minor loss coefficient for the globe valve.
Correct. Yep. Okay. Other questions or concepts you want to cover?
Actually, would you be willing just to go over the equation set up for the special problem 2 of homework 10, just the next equation?
Sure. Okay. So what we have going on here is, once again, 2 reservoirs, and we know that the driving head, right, is going to be the difference between these 2. And the driving head is also going to be equivalent to the head loss. So you can do kind of like Aaron did and jump right to the head loss equation, but for now, I'm going to keep the full-blown energy equation here. So if I go ahead and make this right here 1 and 2, then we're going to have P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G plus P, or equals, sorry, not plus. It's a terrible G. P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G plus the head loss, okay? And once again here, this makes our life easy. P sub 1 goes to 0, P sub 2 goes to 0. Z sub 1, let's see, 2 reservoirs, blah, blah, blah. Okay, so we don't know what this is, but we do know that Z sub 1 minus Z sub 2 is going to be that right there, right? So we get Z sub 1 minus Z sub 2, that's the delta Z that we're looking for. And this one goes to 0 as well. So delta Z is going to equal then our head loss, which is going to be the sum, because now there's more than one pipe. It's going to be the sum of F sub I times L sub I divided by D sub I, we'll put in brackets here, plus the sum of K, those individual Ks, multiplied, oh, I got to be really careful here. The reason I got to be careful is we have different velocities, right? So I can't let it equal one flow rate. So let me back up here. I'm going to have two different velocities. Whoops. V sub 1 over here and V sub 2 over here. So now this is going to be everything multiplied by V sub 1. So I'm going to have F sub 1 times L sub 1 divided by D sub 1 plus, what are the minor losses in here? Well, in my smaller pipe, I'm going to have the entrance loss, K sub E, and I'm going to have an expansion loss because remember the minor losses generally use the higher velocities. So it's going to be associated with V sub 1. So I'm going to have K sub expansion. And all that is going to be multiplied by then Q squared divided by 2G A sub 1 squared. And then plus, now I got to calculate my losses for pipe number 2. So it's going to be F sub 2 times L sub 2 divided by D sub 2 plus, what are the minor losses I have on the downstream side? The exit loss, right? So K exit. And that right there is going to be multiplied by Q squared divided by 2G A sub 2 squared. Now, we already know that K sub exit goes to 1. And because I know the flow rate, I can calculate the friction factor for each of those pipes. I can calculate the Reynolds number, Reynolds number of 1, Reynolds number of 2, the E over D. So I can get the friction factor for both of those. I know the lengths and the diameters. I can look up the minor losses. Okay, I know the flow rate, I know the area, know these guys as well. Everything is known now. So now it's just plug and chug and solve for delta Z. Okay. So the concept here is making sure that you associate the right velocity with the correct minor loss and the correct pipe diameter. So we still only have a single conduit, but we have multiple diameters. So we have to ascribe the friction loss to each one of those and the minor loss to the correct velocity. Now, the reason why I put this in terms of Q is because if I would have used velocities here, then I would have had two unknowns, right? I would have velocity 1 and velocity 2. But by going to a flow rate and incorporating the conservation of mass continuity equation, I can eliminate V1 and V2 and bring that back to one flow rate Q. Now I could substitute those and solve it as well, but Aaron?
How come V1 is 0 and it's stationary there on the top of the head?
Oh, okay. So I just made a big boo-boo. I'm going to call this 0. And I'm going to call this one over here 3, because I have 1 and 2 here. So this is going to be Z sub 0 minus z sub 3 gives me my delta z. And in my equation here, this would be z sub 0, v sub 0, p sub 0. And over here, it would be p sub 3, z sub 3, z sub 3, and v sub 3. So in my reservoir, the velocity goes to 0, but in my pipeline that I've called v sub 2 and v sub 1, those do not go to 0. So yeah, I got a little sloppy with my notation there.
That's where I was confused on that one, is if you just did your Bernoulli's equation from 1 to 2 on the reservoir, you have no velocities to figure out.
Right. Yeah, so all the velocities come into play in our head loss term, and we have two velocities that we need to make sure we take into account.
And that's to get our friction number.
To get our friction and our friction loss and our minor losses. Because the minor loss over here at the entrance uses this velocity, as does our expansion uses that velocity, but the minor loss down here uses v sub 2. And we can't mix those up. If you're not seeing that, you know, this is a great time to raise your hand and we'll approach it from a different way.
So to get the velocity is just Q divided by area.
Correct. Yeah, it's just continuity equation where we say Q is equal to VA. Well, now velocity is just equal to Q divided by A. That's the substitution that we put in to turn this into the flow rate.
And because it's completely full of water, you can use the whole
Right.
area.
Yeah. This is closed conduit. Pipe is full. It's circular. Otherwise, there'd be another set of constraints that we'd have to bring into play. Okay. All right. Other questions? Different concepts?
Could we go over like another rest block type example?
Okay. Sure. All right, let's jump over to so let's stop share for just a minute. Okay. All right. Okay, let's assume that we have an elbow. And it's in the XY plane. Now, the reason why I put it in the XY plane is we don't have to take into account the fluid inside the elbow and gravity, because it has weight. So if I have this elbow line in the XY plane, okay, so here's the XY plane, X and Y, positive direction. I got flow coming in here, so Q in and Q out. And let's Let's add a little bit to this. Let's say that Q out is free discharge. So it's shooting just out in the atmosphere, okay? And we want to know what kind of constraints we need to put on here. So the reaction force in the X and the reaction force in the Y, and then we'll design the thrust block based off of those. But let's say over here on the inlet, we have a pressure gauge and P over here, and P is equal to 20 PSI. And I don't know, this is a 1 foot pipe. Okay. So our goal is to size a thrust block. Well, we know to do a thrust block, we need to get Rx and Ry, so we break these up into their individual components. So we could get the sum of the forces in the X direction is equal to the change in the momentum flux. I'm going to do that delta mom dot in the X direction. And the sum of the forces in the Y direction is equal to delta mom dot in the Y direction, the momentum flux in the Y direction. But in order to get the momentum flux in either direction, I need to know the flow rate and the velocity. Now I know the diameter, so if I know the flow rate, I know the velocity. So the diameter gives me area, right? So I have to know the flow rate. Well, nowhere in this problem have I been given flow rate. I know the pressures because as the free discharge pressure is equal to what? 0. Okay, so P is equal to 0. So I've got P equals 0 here and P is equal to 20 PSI there. And I'm going to make the assumption that the minor slash friction loss is small over this elbow, okay, which is true. One elbow, a couple feet of pipe right there, that's not that big. But I still need to know what is my flow rates and velocities so I can use my momentum equation. Well, this is where I'm going to bring my energy equation into play. I call this 0.1 up here, and this is 0.2 down here. Then I can write my energy, I can write Bernoulli's equation because I'm not worried about the minor losses, the friction loss. So P sub 1 plus Z sub 1 plus B sub 1 squared over 2G is equal to P sub 2 over gamma. Wait, I just having one of those. Okay, this is really stupid. What am I missing here? We normally do this for nozzles, and that's because we have a velocity difference. So my dilemma here is I have to have a head loss to solve this, unless I make it a nozzle. You guys see the dilemma? The pressure here has value, the Z's cancel out, the velocities cancel each other out. It's because I've assumed that there's no head loss. And so I end up with a pressure is equal to 0, and that's not true, right? So typically, the way we would solve this type of problem is we would put some sort of head loss in there. So for example, we could say that K of an elbow is equal to 0.25, and then the velocity inside the head loss would let us get that answer. And which is true, you know, there is a head loss across that. Because now I can solve, these two cancel each other out, z's go, p sub 2 goes to 0, and this is 20 psi. So now if this head loss turned down here, I can solve for the velocity. Or, well, a lot of scenarios like this, I'll flip this back over in just a second. If you haven't caught it, I'll come back here. But think about this. If I have an elbow that comes down and necks down into a smaller elbow. Okay. Well, now in this case, v sub 1 is not equal to v sub 2. So without any kind of head loss, I can make the assumption that there is no head loss and still solve for the different velocities. Or I can solve for a flow rate, actually. The more easier to solve for the flow rate, and then based on the area of this, solve for the velocity in each one of those. Are we comfortable with that? Not? Raise your hand. This is the time to, okay, seems like everyone's comfortable. All right, so but this in this particular scenario, we have to find, so this would allow us to get the velocity, which then allows us to get the flow rate, right? Now moving through this kind of fast, I'm not crunching the numbers.
So why did the z's cancel out?
Because it lies in the XY plane. It lies in the horizontal plane,
Gotcha.
okay? And that's a key part. A lot of students you do the homework and you don't really think about that. But if this lied in the XZ plane, then delta Z would be different. And when I do the momentum equation, I'd have to take into account that there is weight, because it's the sum of forces, right? The sum of the forces, now the sum of the forces in the Z direction, the gravity direction, I have both the weight of the elbow or the nozzle or whatever it is I'm looking at, and the weight of the water inside. So to make it simpler, we just say, oh, it's an XY plane, so gravity, we don't care. It doesn't become part of what we're trying to hold up, okay? So now once I have the flow rate and the velocity, then I can redo my free body diagram. I didn't draw that very well, but so now I've got this velocity going in there, and I've got F P sub 1. I've got a pressure force acting on this area. F P sub 2 down here goes to 0 because the pressure is equal to 0. And I've got a velocity coming out this way. Okay. And R sub X and R sub Y. So let's go ahead and run through, in the X direction. So the sum of the forces in the X direction equals the change. Okay, sure, yeah. Equals the change in momentum in the X direction, right? So what are the forces in the X direction? Well, I'm going to have Fp sub 1 minus R sub X, and that's going to equal the flow out. Well, what flow is going out in the X direction? 0. So it's going to be 0 minus the flow going in. So I have rho V1 Q1, okay? Now I look at this and I say, all right, it's going in, so it's negative, and it's also going in the positive direction, so it still stays negative, okay? So once I've solved for the velocity and the flow rate, now that's the only thing I have in this equation. And remember that Fp sub 1 is just the pressure times the area. So now I can solve for Rx. Let's do in the Y direction, okay? So I'm going to get Fp sub 2, which we said goes to 0, minus R sub Y, those are the only two forces, is equal to then what's going in, what's going out. What's going out is rho V sub 2, Q sub 2. It's going out, so it's positive, but it's going in the negative direction, so this becomes negative. Let me go over that part again. This is the flow rate coming out right here. V sub 2. V sub 2 is going out, so it's positive. The flow is positive. But the velocity vector is going in the negative direction, so I have to put the negative there, okay? And then I look at what's coming in. Well, nothing's coming in the y direction, so 0. So now I can solve for our y. Okay. So now once I've got Rx and Ry, this turns into a statics problem. So I'm going to represent then Rx and Ry are pushing on the pipe, but the pipe is pushing on our thrust block. So Newton's third law, equal and opposite. So if I was to design my thrust block over here, I'm going to say this is my big thrust block, and this is the top view. I have now Rx, and I have Ry, assuming that my directions came out correctly. And I'm pretty sure that that is correct, okay? But these aren't going to flip. And so the elbow wants to move the concrete to the right and up, all right? Now I can go ahead and take those and find then R sub y is equal to the square root of Rx squared plus Ry squared. So I'm going to have some, not Ry, sorry. My resultant, just R, let's call it RR. So my resultant force, RR, is going to equal that right there. Okay. Now, if I wanted to, I could actually find the angle that the resultant force acts, but I really don't care that the angle that acts, because I just want that concrete block to resist the motion. So now I'm in a situation where I have a block of concrete being pushed on by my resultant force, and this block has some weight, and that weight is going to create a normal, and that normal is going to react with a coefficient of friction. So my friction force is equal to my coefficient of static friction times the normal force. And my weight's going to be equal to the normal force. And I just have to take the sum of the forces now in the x direction equal to 0. So I want the reaction force to be equal to my friction force. But I know my friction force is a function of the normal force, which is a function of the weight. So now I can find the weight that I need. And once I find the weight, if I know the specific weight of the material, concrete, 140, 150 pounds per cubic foot, then I can find the volume that I need. I ran through that pretty fast. You want me to write that down? Okay. So I know that the normal force equals the weight, right? So when I come down here, this reaction force is known. So R sub R is known, and that's going to equal the static coefficient times the weight. So now I can solve for the weight. Solve for W, okay? And I know that the weight is equal to the specific weight, sorry, not the specific density, specific weight, gamma times the volume. And since I know the specific weight, now I can solve for, hold on, sorry. Solve for the volume. That's how I know how big my thrust block needs to be if it's on some surface that it, I'm relying solely on the friction force to hold it back. Okay. All right, so I'm assuming we're out of time here. Okay, so we're out of time. See you on Friday. There will be no homework on Monday because we didn't cover any material, but I highly suggest you start reading chapter 12. Should be done with chapter 4, start into chapter 12. Okay? So good luck. If you need to have office hours, please contact me. And we can set up either in office or over Zoom. And otherwise, I will see you on Friday.
There's a class on Thursday.
There is on Mondays and Wednesdays. I don't think they're coming on Fridays though.